Okay, let's keep going. The visual information will go through the two eyes, will go through the optic nerve, which is cranial nerve number 2, and go to the thalamus. From the thalamus, go to your visual cortex in your occipital lobe. And in human, our two eyes are in the front. The reason is the brain needs the information from the two eyes to create the 3D vision. Sorry about that. So when the outside world, which is a 3-dimensional, it go to the retina, which is 2-dimensional. Mathematically, you're going to lose some information. It's mathematically impossible. So what we lost is the depth perception. And the brain used the image from the two eyes to recreate the depth perception. Like when I put the pen here, I close my left eye, I close my right eye, the angle shift a little bit. So the brain need to use the image from the two eyes to create the depth perception. And that's why all the predator, they put the two eyes in the front. So like the tiger, the monkey, and the alien, when I Google predator, this image appear, and we all belong to the predator category. So we put the two eyes in the front. And with two eyes, these are 3-dimensional image. And if they are prey, like rabbit, mouse, and the two eyes are on the lateral, so the one eye see one side, the other see the other side. Their advantage is they can see almost 360 degrees, but they could not have 3D vision, so you could not bring your pet rabbit to enjoy 3D movies with you. Okay, now we're in the auditory system. We're going to talk about the function of auditory system, including the most important one, which is hearing, and also the equilibrium function. These slides show you your ear, including the outer ear, outside, the outer one, including the auricle, acoustic canal. Their function is conduct the sound from the outside to the inside. This part, we call it the middle ear, start from the tympanic membrane. And you have 3 ossicles. Ossicles are the smallest bone you can find in your body. Each one of them is smaller than 0.5 centimeter. And now we have the inner ear, including the auditory canal and the inner ear part. This is the canal. It goes to the throat. Its function is to balance the pressure. When you have middle ear infection, that's the bacteria come from here and to here to cause middle ear infection. It's more frequently found in in kids, because their head is smaller. The physical distance of this is smaller, but it can happen in adult. And this part is the inner ear, divided into the cochlea and the semicircular canal. That's for balancing, that's for auditory. And their nerve together, you have the vestibular branch and the cochlear branch. Together is the vestibular cochlear nerve, the cranial nerve number 8. This slide shows you your middle ear part. You have the tympanic membrane, so the sounds gonna vibrate tympanic membrane. These 3 ossicles, they connect like a hinge joint. So when we talk about the joint, the hinge joint, they push the malleus. And malleus gonna push incus, gonna push stapes. And stapes is gonna push the inside. It connect with the oval window in the inner ear. So they're gonna push. Because the surface area of the tympanic membrane is much bigger, it's about 16 times bigger than the size of the stapes. So it increases the sensitivity of the auditory system. You only need a small sound and you can create enough push to the inside. And now let's look at the inner ear. Inner ear, we're going to spend time talk about the cochlea part. That's the auditory function. And this part, including the semicircular canal and vestibule, that's for balancing, dynamic balancing and static balancing. So we do have people have inner ear damage due to ear infection, and their auditory is fine, but they have problem to balance their body because the inner ear have 2 functions. And we're going to mainly focus on the auditory function. In the inner ear, the receptor, we call them hair cells. They're mechanical receptor. And when the sound comes from the outside, it's gonna push the tympanic membrane and push the inner ear. And when the hair cells vibrate, they transfer the sound into the neurotransmitter release. So everything in the auditory system is mechanical. And that's how the inner ear hair cells look like. They have the hair, and they're gonna vibrate when the sounds come. This one shows you the vestibular complex, and this is for balancing, very similar. So when they also have the receptor like the hair cells, and when you move your head, this otoliths is mainly made of calcium, those calcium crystal, and the gravity gonna pull them. When they pull them, they bend the hair. So they also bend the hair, create a neurotransmitter release when the hair cells were bent. And this shows you the how the inner ear able to sense the movement of the head. So when you move the head, the gravity gonna pull those otoliths and gonna pull the hair cells, and the hair cell will be activated. So that's this part. So inside the cochlea, inside the semicircular canal and vestibule, they all have the hair cells. Okay, the functions. So the function is for auditory, and especially in the cochlea part, the structure called organ of Corti. Organ of Corti. This is like the retina on in the eye. So now let's look at the cochlea. That's the cochlea. We cut it. That's the cross section. So most of this structure are filled with liquid. We call them perilymph in the vestibular duct and the tympanic duct. So most of them are liquid. And in this part, this small area, we call the organ of Corti. I call it sandwich. And this is like the retina in the eye. So now let's look at the organ of Corti. The organ of Corti have hair cells, and these hair cells are like rods and cones, the photoreceptor. So they are the one do the job to transfer the physical stimulus into the neuronal signal. And these hair cells been sandwiched by two membranes, tectorial membrane and basilar membrane. So I call this sandwich. And every time when the sounds come, you're gonna push the inner ear liquid, and the liquid on the top part move in, the bottom part move out. So they're gonna bend the hair, and when they bend hair, it create the neurotransmitter release. So this picture show you the outside sounds come. So in the auditory system, everything is mechanical. You're gonna push the tympanic membrane, and tympanic membrane gonna push those three ossicles, this smallest bone you can find in your body. And you're gonna push the oval window, and that's the cochlea. And when they push, the liquid gonna flow in through the oval window and flow out. So they're gonna bend the tympanic membrane and the basilar membrane. So hair cells being bent. And when the hair cells been bent, it release neurotransmitter and trigger action potential. We're gonna go through the cranial nerve number 8 and go to the brain. So in the auditory system, everything is mechanical. And when you hear the sounds are made of different frequencies. It's pretty unrare you have one sound only have one frequency. So most sounds have a lot of frequency. And apparently you hear the different frequencies at the same time. The reason is your cochlea, that's the basilar membrane, and hair cells grow on it. Different population of the hair cells code different frequency. So say you play a tune, a sound comes, is made of 8 different frequencies. It's 8 different populations of hair cells, they vibrate at the same time. And when they send a signal to your brain combine all this together, and your brain know, oh, okay, that's a cello or that's a violin. So you are able to hear different frequencies of the sound at the same time because of the different population of hair cells. And this is the video. I will leave it to you. And for human, our auditory range is about 15 to 20 kHz. So that's the frequencies we're able to hear. In some animals, like a dog, they are able to hear 30 kHz, 30,000 Hz sounds because their hair cells are able to vibrate much quicker than we do. And when you order the dog whistle from Amazon, and you blow it, you hear nothing because the frequency is 30 kHz. So your dog can hear it, we could not hear it. So again, this shows you our sensation come from our neuronal activity, it does not come from the physical stimulus. Eventually, the auditory signal will go to your brainstem. From the brainstem, go to the midbrain, go to the thalamus, and from the thalamus will go to the auditory cortex in your temporal lobe to be analyzed.